Hey, welcome back, everyone. To close up today's events, Nick Early will tell us about adventures in configuration space.
Okay, well, thanks for the introduction. It's great to be here. I'd like to thank the organizers for the invitation to speak today. So I'm going to be talking about some joint work in progress, and it's been ongoing for quite a few years now on a program related that relates combinatorics, scattering amplitudes, and some interesting generalizations that we found along the way. So here are some of the papers, the archive papers you can see. So it starts back in the background starts back about 12 years ago with two paths, two different paths, and they ultimately converge. So the first path is began in 2013, 2014, when there was a very compact formula to compute scattering amplitudes done by Cachazo, He, and Yuan. So it's dimension independent and defined on the configuration space of endpoints on the Riemann sphere using some discrete integral, some finite integral. Yeah, so meanwhile, I was writing my PhD thesis on combinatorics, representation theory for generalized permutahedra and matroid subdivisions. And I started seeing some connections, some interesting connections to some of the literature on scattering amplitudes that was being developed at that point. And so then I reached out to Freddie Cachazo and in 2018, and we discovered a generalization of the CHY formula for scattering amplitudes beyond M0n to other configuration spaces. So configuration spaces of points not on the projective line, but in projective space pk-1. Okay, so then we worked backward, having this compact formula for scattering amplitudes. We worked backward to try to find a combinatorial prescription for scattering amplitudes, and it turned out that the correct combinatorial description was known by mathematicians since 2004 or so in the tropical Grassmannian, and that's back to what I was doing in my PhD thesis. And yeah, so this is how I got here. And today I'd like to tell you a story about what's been going on since 2018, 2019 or so in this field, and tell you some of the things that are happening now and continuing to develop. Okay, so basic idea is in quantum field theory, in cubic scalar theory, this illustrates a four-particle interaction. Four-particle interaction, and standard property is that when you take a residue, well, you're going to get a factorization of the object into two amplitudes themselves. In this case, two three-particle amplitudes. On the configuration space side, there's kind of incarnation of this, wherein your M0n sort of splits apart, it bubbles off apart, and you get a product of two configuration spaces. So the question is, what replaces this structure when we replace M0n, configuration space of points on P1, with configuration spaces of points on Pk-1? Well, we found some surprises here, and I want to tell you about these surprises, some analogs, generalizations of factorization, and such things. So, okay. So the cubic scalar theory is a toy model. It is modeled on planar Feynman diagrams for the theory are cubic trees embedded in a polygon or a disk with n marked points on the boundary. So it's a toy model, but it contains amplitudes for real theories. It actually does contain amplitude for real theories, as discovered last year and recently by Nimar Kanihamed, Carolina, Song He, and others. So it turns out that from the trace phi cubed amplitude, you can construct quantum amplitudes for quantum field theories, real particles such as the nonlinear sigma model with real pions, pion interactions, and you can get Yang-Mills as well. So real gluon scatterings of gluons. And this is by a process of deformation. You do some deformation of the configuration space, and via the CHY formalism or CGM formalism with my collaborators, then you construct this deformation to get these other physical theories. So the question is, the amplitudes we discovered, what do they deform to? What is the object? What is the analog of NLSM, the nonlinear sigma model, and Yang-Mills that we get under this deformation? And how can we explain the kind of physical properties that we observe? So here's the cartoon, right? What we have is we have a big polytope, some big dimension. In the interior of this polytope, we have the CGM amplitude, this generalized trace phi cubed amplitude. Okay, and on its boundary, we have trace phi cubed, the usual phi cubed quantum field theory amplitude, right? So we found that that's literally what happens on the boundaries of this configuration space. You compute using the CHY formalism, you compute the amplitude and you encounter the original trace phi cubed. So the boundaries are the physical amplitudes. So these amplitudes manifest certain nice properties. Backwards compatibility, usual theories are contained in new ones, and you have a novel factorization property. So we've heard in scattering amplitudes, you usually get like this decomposition on a residue, on a singularity, amplitudes split into two products, a product of two lower point amplitudes. Well, in this case, you get, the first thing you notice is that you get something else, a product into three things. And that seems to violate principles like locality and unitarity, but requires an explanation. So that's like hint number one to keep looking. So, okay, summary of progress. I just want to kind of run through the progress in the program or what we've been learning. So first questions is, it's extremely hard to compute, to use the scattering equations formalism. It's extremely hard to use this, so we need new computational techniques. So what are these amplitudes? They are rational functions of some homogeneous degree. And the question is to calculate and classify their singularities. That's a very difficult problem. We've been making progress on it, and I'll tell you about that. We need to understand what happens when on one of these poles, when you keep only that term. And also in physics, there's a notion of color-dressed amplitudes or color ordering. You want to understand some analog of the color dressing, and this was found as well. So what about progress? The 2018, the first hint of higher structures came through some non-planar analogs of on-shell diagrams, non-planar analogs of Plabat graphs. We saw some hints there. And the scattering equations, and just a few months later, it turned out that we had with Freddie, Sebastian, and Alfredo, we showed that the Feynman diagrams for these generalized amplitudes are encoded by the tropical Grassmannian, especially the positive tropical Grassmannian. So it provides a combinatorial model. So a difficult problem, very difficult, but can we simplify it? Solving the scattering equations and evaluating the CHY integral to compute the amplitude, it involves solving a system of highly nonlinear equations. In general, the number of solutions to these equations is factorial in size, some like n minus 3 factorial. The question is, can we simplify? And so yes, there's a phenomenon called minimal kinematics, where you allow some punctures on the Riemann sphere to start colliding with each other, right? When you start allowing collisions, the number of solutions to the scattering equations is going to drop because the particles can have more freedom to move around. So the number of its critical points drops, and ultimately it can drop all the way down to when there is a single critical point. And to compute the amplitude, you simply evaluate something at that critical point. And that critical point happens to be a rational function, just like just a simple alternating product of linear functions. So there's an open problem here I'd like to invite. Can you extend all these minimal kinematic configurations to higher dimensional configuration spaces? It's a deep problem, beautiful combinatorics, and should have applications to in any scalar theory for k equals 2, and it helps you understand these amplitudes for higher projector spaces as well. So along the way, there's an interesting kind of phenomenon. You take the scattering amplitude and you set some Mandel-Stem invariance to 0, and what happens is that the object becomes a product of 2 or 3 functions that look like amplitudes without encountering singularity. So there's no pole, but the object actually becomes a product. And that is surprising from a physical point of view, maybe unprecedented at the time. But yeah, so we discovered this while exploring while trying to explain what happens with factorization for generalized amplitudes. For combinatorial foundations, to develop some combinatorial techniques for these amplitudes requires some techniques bordering on a little bit to cluster algebras. So the combinatorial foundations for CGM, matrix subdivisions are involved. You get a very special basis of poles that can appear in the amplitude. And there's a combinatorial rule that says, suppose we know a set of all poles, and we would like to know when you take 2 residues on each pole at the same time, when do you get a non-zero number? So that has a purely combinatorial answer, and we'll discuss that later. Okay, so here is sort of from the beginning. So here's why you might think to look for such a thing. On the left-hand side of this triangle, you have physical amplitudes. These are amplitudes computed using a CHY formalism, just usual phi cubed. By deformation, you'll get nonlinear sigma model. You get Yang-Mills, gravity using CHY. On the other hand, on the opposite side, by a flip, by a duality, you get another copy of the same thing. You get another copy of the physical amplitudes. So what happens is you have physical amplitudes on each boundary, and in the interior, you have some new objects which demand to be understood. Moreover, you have inclusion relations, wherein each generalized object includes into the other as some sort of a residue, or more accurately, soft or hard limit for physicists. So if you have a soft limit, you include M5 in there, and so on. Okay. Yeah. Okay, so beyond minimal kinematics, there's another sort of there's another choice of kinematics that allows you to explore even deeper, and it has connections related to cyclic fixed points and positive Grassmannian. So this all is designed to sort of peer into the heart of these scattering amplitudes by taking certain choices of of the kinematic data. Okay, so this whole procedure allows you to look at amplitudes globally, not just termwise, not by a termwise Feynman diagram by Feynman diagram expansion, but you construct the amplitude actually as a global object. That's the global string parameterization. Oh, far into the future, yes. Thank you, yes. So then another problem from before was, oh, I don't see it here. I don't see it on the, can someone? Oh, okay, good. Okay, so yeah. So there are additional structures to be found using the combinatorics of oriented matroids. So if you want to define amplitudes which don't respect a single cyclic order, like trace phi cubed, recall trace phi cubed, the Feynman diagrams for that are trees, trivalent trees embedded in a disk with n-marked points on the boundary. Well, if you want to get orderless amplitudes in general, you need more fancy objects. And these objects are some subfans of the tropical Grassmannian. Chirotopal tropical Grassmannians allow you to compute these in general. So that was joint work with Freddie and Yong, and then a promising student of mine, Dario Antolini. We had a paper on that recently. So I think we're almost caught up. Summary of progress. Okay, so we had this notion of backwards compatibility, right? So these generalized amplitudes, they contain on their boundary trace phi cubed amplitudes. You want a notion of Feynman diagrams to get a combinatorial expansion. And that object is it's called the positive tropical Grassmannian. That plays the role. You need a planar basis. You need some kind of basis for your space of kinematic invariance that is specially adapted to the singularities of the amplitudes. This provides a natural setting to study physical properties such as factorization. So later in the talk, we'll see an application of the planar basis to study factorization for a nonlinear sigma model and such things. Okay. So there's also an analog. So we found an analog of NLSM, and there's also an analog of Yang-Mills in around here too by this deformation. And also let me pose as an interesting open problem that's been in discussions with Nima. There's a stringy analog of all of this stuff. So it's a generalization not just of quantum field theory, but potentially of string theory as well, which satisfies all this factorization properties and more. And there could be an analog of gravity here. Okay, full circle. We have CGM in the interior, trace phi cubed on the boundary, and yeah, so we want to explain all these novel physical features we're seeing. Okay, planar basis. We want to understand factorization. We need some basis for the kinematic space. Okay, so an amplitude is a function of the kinematic data, a function of momenta, P1 through Pn. Momentum conservation says that they sum to 0. Now, the amplitude is a function not directly of the momenta, but of dot products between them. These dot products are called Mandel-Sum invariants Sij. Now, these are not particularly well adapted to the computation of amplitudes. The poles are not just random linear combinations of the Sij's. They're very specialized. And for the trace phi cube theory, they are of a very particular form. And there's a uniform story for all k and n using a hypersimplex. This convex hull of all indicator functions of k-element subsets. So what's the construction? I want to explain how to construct a planar basis of propagators, and that involves some combinatorics and geometry relating to positroids. Okay, so here's the definition. So we have SI is a coordinate function on R to the n choose k. And this is some linear function we define as follows. We have a directed distance function duv on the one skeleton of this polytope. Okay, so given any two vertices on that polytope, we're going to take the minimum lattice distance between those two vertices in steps of E1 minus E2, E2 minus E3, up to En minus E1. That is the coefficient of this SI. The distance from a vertex EJ to a vertex EI in those steps, that gives us an expression for our planar basis element. Now this one can show non-trivially when xj is 0, this is going to be a pole of one of our generalized amplitudes. Yes. Yes. We take steps only in those directions. Yes, yes. But we can get to all the vertices that way. And we take so to hit each time we take the minimum length. Right. So this exactly. So this only in those very small cyclic steps, yes. And so it turns out that this is the correct formulation even for K2, even for trace phi cubed. These when J is a two index, two element subset, this gives you a new formulation for the poles for the planar propagators for trace phi cubed. So here's a little proposition. Using this directed distance function, this is equivalent modulo momentum conservation to the standard formula, the sum of SAB as A and B range from between I and J. Now you recognize this. You may recognize this as if you take the momentum vectors between I plus 1 and J inclusive and take the square of that, then that's the sum over all Mandel-Sum invariants in that subset for pairs of indices in that subset. So here's how it works with the directed distance function. We're computing, here we compute, let's see, so this in the figure is shown as the formula for x13. So we have a 0 distance at the bottom vertex. We take one step up. We take one step to move us to vertex 3, 4. 1 goes to 4 around, and so on. And we fill up the vertices of the hypersimplex with these integer weights. So example is for a 4-point scattering process, then x13 and x24 are linearly independent. and they form a basis for the kinematic space. Okay, these are the non-consecutive xij's. The xij's where I and j are cyclically consecutive, well, we have to, if we set them to zero, that is equivalent to standard momentum conservation, where your end particle momenta p1 plus p2 plus p3 plus pn, when they sum to zero. So it turns out that the cyclically adjacent guys are trivial modular momentum conservation. Okay, oops. Okay, so we give a picture now of the trace phi cubed amplitude. We'd like to come up with a condition to calculate first the trace phi cubed amplitude, which I denote m superscript 2 lowercase 4. Well, this amplitude is the product of is a sum of the reciprocal of the product of the chords 1, 3, and 2, 4. So the two triangulations of a square. These correspond to the two positroidal subdivisions of the octahedron. Similarly, for a pentagon, we start with a pentagon and we have 5 triangulations of that pentagon. Each triangulation has 2 chords in it. And we sum over the reciprocal of the product of the chords for all 5 triangulations. So these correspond to the 5 finest subdivisions of the hypersimplex delta 2,5, or the 5 cones in the positive tropical Grassmannian. Okay. Sure. Yes.
Is S1,2 the same thing as S12?
Where? Oh, yeah. Yeah, it's very non-trivial. It follows from the fact that if you think of these as height functions over the octahedron, then whenever the x1 and 2, when I and j are cyclically adjacent, then when you lift the vertices of that hypersimplex to a slope, to a surface, that slope is constant. No, it's when j is equal to I plus 2. Yeah. But when I and j are cyclically adjacent and I and xij, it's equal to 0. Yeah. Okay, so the amplitude, the trace phi cubed amplitude, it's constructed from this pairwise compatibility condition on chords of an n-gon. So as we saw, the 2 chords x13 and x24 are crossing, therefore they do not appear in the same term. So we like to construct an analog for these new basis elements xj. Turns out there is a notion of crossing. There's a way to say when, generalized way to say when x sub capital J1 and xj2 are compatible. And that's the following. You take the sum of the xi and xj. You think of that as a vector in R to the n choose k. Okay? If the coefficients satisfy this linear identity, then xi and j can appear together in the same Feynman diagram. Okay? So that is equivalent to the statement that if you take EI, where this is the sum of all little a I and I minus the sum of all little j and j of EJ, if that alternates sign with respect to the cyclic order 1, 2, 3, 4, 5, 6 up to n, if that alternates sign exactly twice, then the corresponding propagators are compatible. So the idea of the proof, quickly I'll outline it, is to identify some octahedral face in your hypersimplex delta Kn, which is triangulated, on which is induced a non-matroidal subdivision, in which case this identity would not be satisfied. So it's a little bit of geometric enumerative, some counting arguments, I guess, in isolating an octahedral face which is not subdivided correctly. Okay, so here is the depiction. We have taken n-gon with vertices labeled 1 up to n. Take the difference of the two indicator vectors and put the signs on the boundary of the polygon. Okay, and then you can count the number of sign changes as you walk around cyclically, and you can see this is compatible because it changes sign exactly twice, where we forget the zeros, right? And for like 1, 3, 5 and 1, 4, 6, well, that changes sign 4 times. For 1, 3, 5 and 2, 4, 6, that changes sign 1, 2, 3, 4, 6 times. So these are incompatible, and this is equivalent to the notion of what's called weak separation in cluster algebras. So the point why I'm drawing this is that these are actually, you should actually think of weak separation as being embedded in these relations as being embedded in the hypersimplex as sort of long diagonals of a cube. Anyway, that's the principle. Okay, so a key theorem here, you need to show that all of these propagators we construct with this directed distance function, we can show that they're linearly independent. And in fact, they form a basis for the kinematic space. Okay, so what are some key features here? How do you prove, how do you write the proof? Well, in the case k equals 2, you have the simple formula, alternating formula. Sij equals this summation over the vertices of a sort of cube here. Xij, xi, negative xij plus I, j minus 1, etc. You have this alternating 4-term summation. The idea of the proof is I want to take any original Sij and expand it in terms of the xj's. Okay, so I need a formula to do that. And so yeah, the formula in general is an alternating sum over the vertices of some d-dimensional cube. So it's kind of a big identity, but combinatorics is pretty rich, and we can use that to construct even more interesting objects on the configuration space. Some applications. So just as on the configuration space M0n, you can define certain cross ratios. So cross ratios describe they give a natural set of coordinates on the configuration space M0n. Well, it's not clear a priori how to get analogs of cross ratios on configuration spaces of points in pk-1. Not clear, but it turns out there is a way to do it. And this procedure, it controls factorization properties for generalized amplitudes. And it organizes a singularity structure. And it's all an artifact, a consequence of having this directed distance function. So like everything seems to flow from that for when you're in the realm of the positive configuration space. Okay. So the notion leads to a notion of, we have a notion of compatibility for planar basis elements. If you take, they are compatible if and only if they generate a two-dimensional cone in the positive tropical Grassmannian. So this is non-trivial. Remember, we want to write, just as we had for a polygon, we compute the trace phi cubed amplitude by summing over all triangulations of that polygon, where we take the product of the reciprocals of the chords, right? So we have this analogous rule here. We want to take, when we have a combinatorial model, sum over all non-crossing collections of xj's, and construct the amplitude in that way. And so that's what this simple condition provides. Not so obvious, actually. So imagine it's not obvious because in general, the amplitude here, generalized amplitudes, have many propagators that are not planar basis elements. So in principle, xi plus xj could decompose another way. In other words, it could be that if you think of xi and xj as vectors, you have this xi, this xj, that could be equal to two other guys that sum this way, right? But that does not happen in this case. So this notion of compatibility it does work well. So that's if you impose this notion of compatibility, this is just an enumeration. You see on the boundary here, on the two boundaries, we have the numbers, the Catalan numbers, which is the number of triangulations of an n-gon, the number of Feynman diagrams in trace phi cubed. And in the interior, you have the corresponding numbers of maximal weakly separated collections, which correspond to maximal collections of propagators for generalized amplitudes. You can see it grows pretty quickly, and I could not fill in those middle, that proved to be too much for my computer to fill in those two rows there. But. Okay, so now we move to an application. Sure, thanks. Yeah. Yes. Yeah, so it's very important to explore that too, yeah.
The same flipped graph. I mean, all these different flipped graphs are from the same fundamental set. But it does say they're actually from different colors. Every maximum collection.
Yeah, it's so it's the same structure, but the geometric consequence, the geometric role is quite different, yeah. Say again?
You know, the flipped graph can take any flipped graph. So they're all
Yeah.
Your one should actually represent different colors.
Yes, exactly. So each Plabat graph gives you some cone in the positive tropical Grassmannian. Yeah. And it also gives you some particular like product, 1 over some product of xj's that would contribute to the amplitude. Okay, so I'd like to go to an application. So what can we do with this planar basis now that we have it? Well, the application is to generalize not just trace phi cubed, but the nonlinear sigma model. So for that, so we have this natural system of coordinates on the kinematic space, replacing not just Sij, we also replace Xij, which is this squared sum of momentum vectors. Now we're going to get a generalization, a natural set of coordinates on this configuration space. And these coordinates will define analogs of factorization, bubbling on this configuration space, just like we had bubbling where in moduli space M0n splits into two pieces. Well, In this situation, the WJs tell you how to do that. And they'll also control the singularities of these amplitudes as well, meaning simple singularities, meaning like simple poles and rays of the positive Chaproux-Grassmannian. So yeah, this planar basis for k equals 2, you can discover NLSM inside of trace phi cubed, as done by Nima and Carolina and collaborators. And we get a generalization using the planar basis to higher k, new understanding of factorization. So this geometric framework, which we've developed in the past 6 years or so, it's really illuminating the physical principles here. So here, let me give you the formula for the trace phi cubed amplitude. You take, for any tree with boundary labeled 1, 2, up to n, for any such tree, you take the product over the internal edges. To each internal edge, you associate 1 over a propagator. You associate a propagator like that, and you sum over all guys. So the key insight is that if you take a deformation of the internal edge propagators by some parameter delta, say send xij to xij plus n times a parameter delta, and then expand around delta equals infinity, expand this expression around delta equals infinity, then you get an amplitude for a real physical theory for pions. So it turns out in this case, for Mn delta, there's only 1 degree of freedom. Like if you want to do this, there is exactly 1 choice. I can't take any other. What I'm saying is the condition that NLSM, condition of the deformation, fixes Nij to be exactly this expression. There's no other choice. This or it's negative. That's it. The situation is much more complicated, much more interesting for higher k when we have more degrees of freedom. See that in a second. For n equals 4 particles, then n13 is equal to 1, n24 is equal to -1. And in that case, we take the 4 particle trace phi cubed amplitude, take the deformation, x13 goes to x13 plus delta, x24 goes to x24 minus delta, take the expansion around delta equals infinity, leading order term cancels, and the coefficient of 1 over delta squared is the NLSM amplitude. It's kind of a miracle. They show that that procedure generalizes to all n, of course. So let's move to the, so we're going to have a little interlude here now. Transition from k equals 2 to k equals 3 NLSM. We need to motivate, we need to give some motivation. Okay, so what have we seen? We start with a planar, the Mandel-Steffen invariance Sij. We discover the planar basis Xij. You can either get it from the standard formula by taking the squared sum of a set of momentum vectors, or you can come with this directed distance function and you have a closed formula for it. And once you have that, we put it into this so-called scattering potential. And we want to solve this scattering potential for the Xijs. We can do this because the Xijs are linearly independent, right? So Xijs are linearly independent. That means we can extract the coefficients of them in this linear combination. Those coefficients are going to control the behavior in the moduli space. In the moduli space M0, and those coefficients are the so-called U variables. So they embed M0, the real moduli space M0n, into some cube, and that just characterizes a binary geometry. We want to generalize this to k equals 3. We can do this. We need the planar basis, xijk's. We need the k equals 3 analog of these cross ratios. right? And then we need a generalization of the CHY formula. We need a generalization of the scattering potential. That's kind of obvious to write down, I guess. Take the logarithm of each minor, each 3 by 3 minor in a 3 by n matrix. Multiply by a number, the SIJK. We have momentum conservation relation, the n relations where for each value k equals 1 to n, you sum over all other pairs. That's equal to 0. So the key insight again is that the XIJKs are linearly independent, so we can calculate their coefficients in this sum. Those coefficients are called planar cross ratios. Then we're interested in, we'd like to understand, it's an important problem to understand what happens when one of those goes to 0. What happens to the values of the other planar cross ratios when one of them goes to 0, right? That's an important problem, has an answer. But let's give some explicit expressions. U24 first, P13, P24 in the denominator, etc. At k equals 3, well, you no longer have only quadratic cross ratios, you always also have this degree 4 cross ratio. So rule is, if you look here, you see that P135 appears here in the denominator. And you look in the rest of the denominator and you see that the other indices skip in pairs. Cube. Yeah, okay, yeah. Vertices of a cube, yeah, exactly. And so what's the key difference from k equals 2? Our deformation space that was used to construct NLSM, that was one-dimensional. Well, it turns out our new deformation space, in this case, is two-dimensional. And it has, it's generated in the following way. If 3 and n are relatively prime, there is no solution whatsoever. Just trivial solution. There's no deformation. If the GCD of 3 and n is 3, then you're in good shape and there is a deformation. So if 3 divides n, then you're fine. And you get these, this is the explicit formula for the solution. In the case n equals 6. So it's like you take, for arbitrary n, you take 1, 4, 7, 10, 13, 2, 5, 8, etc. You take all 3 of those, they sum to 0. From these values, we're going to construct a deformation. So the values for n equals 6 are as follows. There are 4 guys with value +1, and 4 guys with the value -1, and the others are 0. It has to do with the size. So we're counting the size of the intersection between I, j, k, and the set 1, 4, 7, etc. It is what it is. I mean, you got that. I got that by solving some system of equations, but that's what it turns out to be. Okay, so we'd like to understand, remember we had our scattering potential. It was written as a linear combination of x's. Well, we can take a deformation of that scattering potential, and it transforms in this way. We add a delta times a logarithm of the product of all wijk's raised to some integer powers. And in this case, this nasty product, which you might not imagine would be very simple, actually is. It's very simple. It is just this product of 4 cyclically consecutive minors. So you can see a new way to construct this, and you can start to see why this divisibility criterion is so important. So in general, these factors that you get, you're going to take the set of all cyclically consecutive triples, 1, 2, 3, 2, 3, 4, 3, 4, 5, and 1, 2, and form all ratios, all ratios of products of these that have torus weight 0 on each index. And so, yeah, then these form a multiplicative basis for that space, and that's the rule on the ends. This rule here gives you generators of that space. So you need you need 3 to divide n. And you'll note that this deformation, it preserves the residue structure. It preserves the factorization structure. So any operation we do on the generalized trace phi cubed amplitude, it's going to work in the deformation. Okay, so case K2, K equals 2, we know. So recall that the amplitude is this product 1 over x13 plus 1 over x24. We'd like to, what we're going to do now is I want to give you the generalizations of NLSM amplitudes. I'm going to give them, I'm not going to give you the whole thing, I'm going to give you the residues. That'll fit nicely, and we'll recognize these residues immediately. So, right, we get, what do we get? In the planar basis, for M6 to M36, okay? So this comes from 6 points in the projective plane. The amplitude is a linear function of homogeneous degree -4, happens to correspond to the dimension of the positive tropical Grassmannian modulo lineality. Okay, so there, in this space, there are exactly 2 kinds of singularities of the amplitude here. One is what I call a 2-split type. There are 12 of these. They can be written, if you modulo these momentum conservation relations, you can write them in the simple way as S123 or as a sum of these guys. There are also, what you have is if you take a residue of this amplitude on x236 or x346, then you get something which is, in the case x236, you get a copy of the 6-point trace phi cubed amplitude. You get one copy of it embedded on that residue. Similarly, for its cyclic shifts, if you take the x135, take the residue on x135, then you get product of 3 trace phi cubed 4-point amplitudes. That's shown at the bottom here. And similarly for x346. Okay, so we're going to take this deformation and then compute some residues. So studying residues reveals some novel structures. So 2 fundamentally different types of residues appear. We'll see we have a mixing between NLSM and trace phi cubed. So one residue, we get a 4-point trace phi cubed amplitude and 2 4-point NLSM amplitudes. Remember, the NLSM amplitude, the 4-point guy was S12 plus S23, or in other words, X13 plus X24. Okay, so this is showing already an unexpected connection between the two theories. The X346 in this deformation, remember we're taking the deformation where delta goes to infinity. Well, we get this rational function. Maybe that doesn't look nice, but when you compare it to the 6-point NLSM amplitude, you see it's on the nose, up to a sign. So we get the sum of S12, S23, S34, the cyclically adjacent guys pairs, and then we have these 3 sort of products of 4-point NLSMs, and you can see exactly the same structure up here. The deformation, there's a second interesting deformation. If you take generic, like a totally generic guy, take the x's to be generic, complex parameters, say, then you get this. And every residue now is a product of 3 pure NLSM amplitudes. So it's all the same, right? Here it's a miracle in this case that the x, y, and z just factor out entirely. But so we get this totally generic deformation, and you get this pretty nice generalized amplitude that has this recognizable residue structure. Wrapping up slowly. So we have this planar basis. We have they provide a natural system of coordinates on the kinematic space. controls the notion of factorization channels. I'm going to take some, we have the S, T, and U. S equals S12, T equals S23. Those are crossing channels. In other words, they are two crossing cores and n-gon. They're incompatible. Well, we have the generalized notion of that compatibility in our story. We have a notion of planar cross ratios. So these are like U variables for this higher configuration spaces. They are deeply connected to the planar basis via the scattering potential. The K equals 3 deformation structure is non-trivial only when 3 divides n, and it's generated by these two shift parameters, 2 out of 3. So what we've seen the two-dimensional deformation lattice. We found NLSM inside of trace phi cubed. We've seen a very rich interplay between geometric structure and physics. We're seeing that the boundaries of generalized amplitudes are trace phi cubed amplitudes. I mean, trace phi cubed is found on the boundary. What are some key questions ahead? We're going to need to evaluate both higher n when k equals 3 and higher k. I expect that the behavior will be richer and richer as we increase these things, and we'll see more and more kinds of new phenomena. We need a complete classification of the singularities of generalized amplitudes. If we impose some notion of positivity and look at positroids, then it'll be possible, a plausibly finite task. I think it should have a beautiful solution. We'll need to look at connections to other quantum field theories beyond trace phi cubed and NLSM. And wrapping up. So here's a diagram, right? We start with trace phi cubed. We have some deformation process to get to NLSM. There's a different deformation process to get to Yang-Mills and eventually gravity. So we have this funny symbol, introducing a new symbol. It means that trace phi cubed is included and is generalized by CGM. So it's included on the boundary and it generalizes. We get new phenomena like generalized factorization. We have this deformation going down. We get an NLSM analog of CGM by deformation. So there's some generalization of spontaneous symmetry breaking. Work in progress is to generalize Yang-Mills and eventually gravity. So we have some generalization of gauge invariance, generalization of diffeomorphism invariance, and thanks a lot.
Questions for Nick?
Yeah, so it's a question, comment. So you have these maximal weakly separated collections, which kind of appear under various guises in different places. For example, there are exactly base labels of Lebesgue graphs or clusters of certain nice clusters of cluster algebra on the Grossmanian. What I want to say, so we had a paper with Miriam Farber, which is called arrangements of equal minors, which is kind of some collections of subsets, and these weakly separated collections are kind of one extreme things, but interestingly we have the kind of opposite extreme, which is also interesting, which is kind of maximally kind of interlaced things. So if you have two minors, the indices should be just literally interlaced. And we're looking at maximal things like this, and surprisingly, they also related to the same story, kind of from a different point of view. I'll probably kind of explain in my talk. So they also related. So basically, they give alpha of triangulations of the kind of simplex, for example. So somehow this kind of, I'm just wondering if from physical point of view, or like from this point of view, it makes sense to kind of go to the opposite extreme instead of combining things which are kind of separated from each other, combining things which are kind of as interlaced as possible.
So yeah, that's a very interesting.
Natural, and it's kind of really relevant. And two nice cases, they're very different, but somehow they're kind of linked to the same thing.
So that's a fascinating question. So I think that they do have a role. So at least one role that I found was that in the construction of new rays of the positive tropical Grassmannian. So if you take it's not exactly, but so if you take some collection of k-element subsets which is pairwise not weakly separated, so each, in pairs that they have a pairwise violation of weak separation. Yeah. That, especially in that case. Yeah, then there is a recipe. I proposed a recipe to construct a very exotic family of rays and propagators from that data. Yeah, so it involves a you have to use a tropical measurement map to do it. Yeah.
So in thinking about the sense in which there's a generalization of gauge symmetry, or even in the sense, so the gauge, there's some kind of generalization of spontaneous symmetry breaking, which is physics, so this like cosets, G mod H. For pions, the ordinary LSM, the Lie algebra structure there, we understand how it's encoded in the amplitude. It's encoded in what happens to the amplitudes, very well in the limits, because some of the momenta of the pions are zero. So some factors you sometimes get zero.
If you just have one pion, you get zero. If you have two pions, you get an interesting factor, and that factor is actually reflecting the Lie algebra. The precise factor you get is an avatar of two generators commute to give you a generator. And then something happens with 3, 4, 5, and so the sort of pattern of what the multi-soft limits are is the amplitude avatar of the exponentiation of the small Lie algebra elements to full group elements. My question is, the most fascinating thing here is what are the okay, it's one thing to have some funky generalizations of the amplitudes, but what gives it, makes it seem potentially a lot more exciting is if it comes along with some generalization of Lie algebras, some generalization of diffeomorphisms. We're talking about gravity and gauge symmetry and so on. But the sort of first clue, the sense in which it's generalizing these things, would be to look to see what the soft zero or the multi-soft factors actually look like in your LSM example. So for example, the most basic thing to see the non-commuting feature is if you have like a pion here and a far away pion here, they're separated, then their limits are independent, but if they're next to each other, something happens, right? So you get an interesting factor. That's the most zeroth order aspect of the non-commuting phenomenon. Do you know what the analog of that for you is? I thought for you, does something happens in single soft, double soft, triple soft? Does it depend on whether more than one of them overlap? Do you know anything about what the multi-soft limits look like for your?
So far, I have some ideas, I guess. For the thing I can say most is that there is a dependence on the GCD, and there's a dependence on the direction of the deformation, right? So if we take totally generic, then I don't know. It could be that we need to take 3 particles or something.
In the case of the NL7, the standard deformation was kind of associated with the fact there were these zeros between the different degrees in the deformation, as well as these splitting features, which in certain cases are actually related with these multi-soft limits that Ima is hinting at. Is it true that these sort of features are also there for your generalizations, like the zeros or slash the splits?
Zeros, what role do the zeros play, you're asking?
No, deformation is the only deformation that you can do that preserves the zeros for all units.
So, yeah, so it turns out that, if you ask that only, yeah, the solution space is two-dimensional if you want to preserve the zeros of k equals 3 amplitudes, yes.
It's the same.
Yes, yes. And it depends on the GCD. The more generic, what I can also say that like, the more generic the deformation, the more propagators disappear or sent to infinity and no longer appear as a possible residue. Right, so the soft limit there would be even sparser, sort of.
So anyway, the concrete suggestion is to try to pull off, I mean, there's the zeros, but then there's some actual factors that you pull off when when you're emitting more ion, yours or ours. And the functions, those soft factors carry some information about the Lie algebra structure. So you should be able to figure out what that means and what its exponentiation might mean in this context.
Yeah. So like, I guess you might need triple. Yeah, you need triple things. You have this.
Might not just be when pairs are close, but maybe
I
triple
think
octals.
it's gotta be that, because you have to get down to the next time n is divisible by 3. Yeah.
Yeah.
I'll take it offline.
Okay, then let's thank the speaker and let's.